So today's class is going to be rather informal, and it's to show you how to use this other software that does things, well, A, that's free, and B, that does things that SPSS, if it can do them, it doesn't do them easily. Whereas this other software does these things very easily. As with a lot of things when you're dealing with different software, sometimes you have to structure your data set slightly differently and so on. So I want to take you through that. If you have the factor demo data from Tuesday's class, we'll just use that. How's that sound? Yeah. Woo! Oh, I am using the 64-bit version. The top one. So I did some things just to make it slightly easy for us. I reduced it only to the questions, only the variables that we are using. So there were 12 variables. Of course, if you were doing a real data analysis, the chances are you would have an ID variable and some other things in there. But for the purposes of today, I've reduced it only to the 12 variables. And for those of you that are unfamiliar on how to code missing data, you can go to recode in the same variables, select everything. The old and new values are, oftentimes we're just trying to get them all to be one value. So system missing is when it's blank. User missing is when you've told SPSS it's a certain number. But I'm just going to select both. And then I'm going to say the new value is 999. Now, I was expecting a small uproar there, but it didn't happen. Because I'm a big negative 999 fan. But the software can't handle a negative value for a missing value. So I'm stuck here with 999. But 999 is big enough to cause big problems. And that's what you want. Like your factors, you'll look at your means and you'll be like, why is that mean so huge? Why is this thing? And it drives you into the data if something isn't quite going right. So that's what you want. So once we've done this, now we're going to output it as a .dat file. So file, save as. We can keep the name factor demo, but let's change it to a .dat tab delimited file. Now, if life were good and easy, we would just click save. But we need to uncheck write variable names to spreadsheet. It's just going to be the little integers. This, once you select tab delimited, then you can uncheck that box. I thought wait, what problem are people having? I hear murmuring.
Well, it doesn't just say save, it says store file to repository.
Yours says store file to repository right here?
Oh, save's on the right.
Oh, here's what you have. Got it.
Yeah, and then that's in the
I already have it on the desktop, but I'm going to write over it. Now, don't close SPSS yet, because there's one other thing that we want to do. We can have variable names in the other file, like when it's doing the analysis, but they have to be saved to their own little file. So what you do is you go to variable view, and maybe if the variable names were better, you'd select those. Let's use the labels. I think that'll work. So I'm just going to copy those. And I'm going to open up a text editor. What's it called in Windows? Notepad. If you're using a Windows machine, open up Notepad.
How did you change all the values? The 0 to 999?
That was the transform, recode into same variables, select all the variables, all the new files.
You add it.
Keep going. Keep going.
It-
Yes.
Okay. You with me? Yeah? Okay. You can do it manually.
Sure could.
Oh.
Sure could.
It's writing 999 about 20 sometimes. That might be tough, but
It's a hard pass, but I'll follow.
okay. Okay, so you've got the variable. I'm using the labels. You open up text editor or Notepad. Just copy those in there. Let's do. I'm going to save it. We want it to just be. Wait, I guess rich text is what. I guess I did it in Notepad before. Why can't I just do dot text? What? I would call it something like labels. Now we should be done with SPSS, but I'm just going to minimize it. Oh no. We're going to be fighting this all class.
Do 4 hours.
4 hours. Now we're running Windows. It doesn't seem right that labels is ELS, but I think it is. Labels. So if you've downloaded that software, we should have what we need. Now, at any point, if you get confused in this, there is some help available. It's kind of, where is it? Oops. Well, I'm just going to show you. I really thought there was another thing. Oh, and this is why it's a good idea not to close SPSS, because you're like, wait, how many participants were there? And so you go over to SPSS, and you say, oh, there are 21 rows of data. So that's what goes here. And then, how many variables are we working with? 12. Now, if you had other variables in there that even aren't going to be included, that would still go in there, although it may make a lot of sense to just run your factor analysis in this as its own little standalone thing, and then go back to doing everything else in SPSS. But nonetheless, for today, it's 21 participants, 12 variables, and it wants to know where to find the participants' scores. So it's looking for a .dat file, and I saved it as factor demo. Rachel, is everything okay?
I'm just gonna see if it uploads or not.
Okay.
I couldn't find that file.
You can also choose to run it as a variance covariance matrix, and if so, you would check that and enter it that way. I've never done that, but presumably it's not very hard. We do have some variable labels, and so you're going to check that box. You're going to browse and select labels. Notice it's looking for a text file. And then here's the missing value code. And I know because it took me 3 times. I was like, oh, 999, it's negative. And but I don't know, I had the sound down or something on my computer because I didn't notice that it didn't. But I it was like, boom. And then I ran the analysis. And I'm like, why are the means so freaking wrong? And I was like, I went back and I was like, oh, it's 999. I guess I didn't hit. So I do it again. Anyway, I'm an idiot. So it took me until the 3rd time to realize, oh, negative doesn't work. So change that to 999 or whatever missing value code you're using. And then click OK. So we have now configured the analysis. It's like, this is where to get the data. This is where to get the labels. These are how many participants to look for. This is how many variables you're looking for. And so we've prepared the program to run the analysis, but we haven't done anything yet. And so now we go to, oh, sorry. So that was read data. Now we go to configure analysis. And this is where things get a little bit more exciting. So right away, you'll notice by default, it includes all variables that are in your data set. And you don't move them over to include them, you move them over to exclude them. Notice that's just a little bit different than how SPSS normally works, so it can catch you off guard. So if you had like a naming variable, or an ID variable, I mean, you'd put that over and exclude it and anything else. A good starting point is just with a Pearson correlation matrix. We're going to come back and talk a little bit about this polychoric one. But notice this. It has this built-in procedure to help us figure out the number of factors. And I thought that I had a dry erase marker in my bag, but I do not. Does anybody have one that I could use? Throw.
He knows where
If you're gonna do that, you gotta stick it.
Yeah, you got it.
Are we gonna have to do this for homework? Use this program.
I was thinking about it.
To be honest, I haven't completed writing your homework. So. I'm getting a grant, and but these things, it's like they've got it for 8 months, and then they're like, okay, we're recommending you for funding. You have 3 days to answer these questions to get us all these documents. So
We don't have to do homework this week.
Really?
It's all to you.
Yeah,
Yeah.
for your sake. I think that's something you should do.
Yeah. We can just help you with the grants.
all right. So I mentioned this the other day, but I wanted to take a moment here to explain it just a little bit more. What a parallel analysis is doing. So this is a data matrix. This was obviously a very small one, but it would apply to anything. Now, when you're doing a factor analysis, it is extracting eigenvalues from this matrix. And remember, what an eigenvalue is it's a reconfiguration of the variance into chunks that are as big as possible. But because variance has a total, ultimately you're going to wind up having all of the eigenvalues equal the number of variables, and so the total stays the total. So some eigenvalues are going to be much bigger than the variance of any variable, and some are going to be much smaller. What we care about are the bigger ones, because the bigger ones, what that means is that eigenvalue represents a linear combination that captures more variance than any single variable by itself. But eigenvalues over 1 is really the minimal threshold. And what that's saying is that any eigenvalue there and its associated eigenvector loadings, any variable or any eigenvalue greater than 1, what that means is it's explaining more variance than any single variable. But you know that there's error in here, and there are random fluctuations of data. And so some of those eigenvalues might be greater than 1 by chance. And so parallel analysis is a way for us to determine how many eigenvalues, the values that you can expect just based on chance in your data. So what it does is it takes your data set and it randomizes all the values in a column. Here, here, any one that's included in the analysis. It randomizes its place. And so what that means is that for ID1 here, these values, at least likely, aren't ID1's values at all. But it's going to randomize, and then it's going to do a factor analysis. Now, the factor analysis, now, any of those associations are there by chance, because you've randomized everything. And so it computes eigenvalues, a complete set of eigenvalues. And by chance, some of them are going to be quite large. But it doesn't just do that once. It does that, let's say, 500 times. It randomizes, and it does a factor analysis, giving us eigenvalues. And so what this does is it gives us a quantitative way to evaluate the eigenvalues in our data set, the real ones, the non-randomized ones. It gives us some sort of benchmark. So there's the eigenvalue from the data set, and then there's the eigenvalue that's from the random draws. No, it's not a draw. It's an actual randomization. And so we're going to have eigenvalue 1, eigenvalue 2, 3, 4, all the way down until you have the same number of variables. And what you do is you compare the eigenvalue in the data set to the eigenvalue that you can expect just by chance. And if this E is greater than this D, then you say that's a winner. That because it's giving you more variance than you'd expect by chance. What about the second one? Is that one bigger? Sure, why not? But if you get to the point where it's less than, now you say we have two factors. This eigenvalue could be 13. It might be some huge number. And yet, if you can get 14 just by chance, then you really can't say that that's a real factor. So parallel analysis is a data-driven way. Notice the other things that we were talking about, it's like a scree plot is like mildly data-driven, but it's all about like look at the loadings and see if the things are holding together in a theoretically relevant way. This is a much more hard-nosed, data-driven way to do it. And one of the things that I love about this program is it has this built-in parallel analysis. And that data stuff that we had to do, to me, at least to me, is very minor. That's easy. And so I would actually recommend doing factor analyses in this program. Yes?
Randomization, does that return the greatest eigenvalue out of those 500 iterations or the average?
It's so cool. You're actually going to get the mean from those 500 and a 95% confidence interval. And notice your interpretation might vary. Which one you use is actually up to you. I'd say most commonly I've seen people use the mean as the benchmark, but you can definitely see an argument for a 95% confidence interval as well. So we can configure the parallel analysis. Notice I'm actually not going to. I think the defaults in here make sense. So you have a choice about whether to use some normal distribution or to actually use your data. I'm going to say go ahead and actually use your data because then it's your data. That makes a lot more sense. And 500 is a good number. You could try more if you felt like if your numbers were kind of really close to a cutoff or something and you wanted to firm it up a little bit, you could try that. But particularly with a data set this small, I don't think it makes a lot of sense. Now, I'm going to start with saying extract zero factors. And essentially what that means is it's going to do an exploratory factor analysis, but it's just going to do the parallel analysis. It's not going to actually give us the weights. That's all that really means. You can do a PCA or unweighted least squares, maximum likelihood. I don't know what this minimum rank factor analysis is. But the website has more information about this. But they are actually doing a missing data technique, which, think about it, SPSS isn't going to do that either. So it's really not a bad way to go. Okay, so I'm going to click OK. Is everybody up to speed with me? It gives you that warning saying factor components will not be computed, but that's fine. So that's in the configure. We have not run it yet. It does not run until you click compute. Boom.
They are in Spain. We can't win.
Wow. Wow. There's a lot of hostility here.
Unrestricted factor.
So, in some ways, it's a recapitulation of what you of what we already input. Here it says that the multiple imputation method it's using is hot Dex sampling. Do you guys know what that is? I see. Who doesn't know what that is? Okay, let me explain. Hot Dex sampling is simply in your data matrix, it's saying, we've got a missing value here. Which value should we use? And what it does is it randomly selects another person's value to pop in there. And so anytime you have missing cells, it's saying, well, what's a good guess? Well, somebody else's value. So there are other imputation procedures, obviously, that are going to do something very different. They're going to say, well, what's the mean? What's the standard error around that mean? And it's going to try to make a guess that way. Hot Dex sampling says, let's just use somebody else's value. My understanding is that it's doing that again and again and again each time it's running one of those parallel analysis. So on average, you're going to recapture the mean and recapture the standard deviation in your data. It may not do that for every instance of it, but on average it should. Because the average and the standard deviation is based on those other values anyway. Okay. Notice our variable labels worked. Isn't that nice? So now we can directly look and say, well, and you remember they were on a 0 to 10 scale, so these means make sense. It even gives us a confidence interval around the mean, which we may not be used to. It gives us some stuff to consider. I'm not going to get into all that. It gives us multivariate descriptives, which is something we didn't even really talk about in class, but it is mentioned in the book. They're a little bit, let's call them exploratory. They're not hard and fast statistics like some of our other univariate ones. It gives us a variance covariance matrix. Oh, and this one is standardized, so it's correlations. And here we get to things that feel more similar to what we get in SPSS. So we get an eigenvalue from the data, and we get the variance explained. We get an eigenvalue, and we get the variance explained. I didn't actually directly compare this to the SPSS ones, but they should be similar. Maybe we should. Oh, there it is. So here we get 4.22, 2.15, 4.41, 2.99.
Could you just scoot that? We don't know what it says before variance.
No.
Explain variable. Explain variance.
We can only see.
So look at on the screen. You can't.
it just says ED variance based on eigenvalue.
Just like
And
the
ED,
last.
so we just want to see
Like
that whole word.
scoot the little.
There. Thanks.
Whoa.
Is that hard to maintain?
I can't hold it any longer. Okay. So these are not the same as the ones we get in SPSS, but that doesn't surprise me because SPSS is only using the observed variables, and we also have a different estimator here. So they're close, but not the same. But the question is, that 1.96 really is the only one that's over 1. But really, and close to 1 though. But are these just expected based on random fluctuation in the data? And that's where we get into this part at the bottom. So it switches to percent instead of just using the raw eigenvalue, but those are interchangeable. So what it is saying is that that first factor, you can, out of your data set, you were able to explain 37% with it just by random parallel analysis based fluctuations in the data. You can get 24.5% out of your data, which is a lot. But you will notice that 37 is definitely more than 24.5. Now, this is, I already alluded to this, it gives us a 95% confidence interval. Now, we don't care about the low end, which is why it just gives us the high end. The 95% confidence interval for this random percent of variance is 29.4. So 37 is bigger than 24.5, which is the mean, but it's also bigger than even the 95% confidence interval. It's almost like a statistical test, almost. I mean, it's as close as we're going to get to saying that that eigenvalue is like statistically significant. And this is where we get the asterisks at the bottom. Advised number of dimensions when the 95% confidence interval is considered. So it's saying that one is bigger than 29.4, which is the 95% confidence interval. And notice 25% of the variance. That is bigger even than the second one, which can explain 22%, 95% confidence interval. It's the third one where we actually have a decision to make. The third one, the percent of variance explained is 16.6. But you can get 50, the average third eigenvalue out of the parallel analysis can give you 15.1. And in fact, if you look at the 95% confidence interval around that 15.1, it's 17.2. So here, the 16.6 is greater than the mean, but less than the 95% confidence interval. And like I said before, I've actually seen the mean more commonly reported as the comparison than anything else. But what this really tells you is that we should consider 2 and 3 and look at the data and to see. Now, we've already run these analyses. And do you remember SPSS? It was like, ooh, kind of looks like 3 maybe. But because I know, and that's an option. But I know from actually how I designed the measure, and if we look at bigger data sets, I know that it's really 2. But this, in some ways, is like a beautiful thing because it confirms that. It says 3 is kind of there, but if you just consider how much noise is in a small data set like that, 21 people. That is very small for an exploratory factor analysis. But I'm still able to find the right structure if I use that 95% confidence. And that, to me, is impressive and very cool for a little free program that you can get. There are probably some questions. Rachel.
I feel like I'm mixing up a little bit in my head, but comparing this to last class, would these 2 factors kind of indicate they're rotated or unrotated?
So, your decision about the number of factors has nothing to do with whether it's rotated or not.
Well, that's totally our interpretation.
Yes. Well, I suppose I should put a little caveat on that. So let me say a little bit. So a rotated solution helps you interpret your factors. And how you interpret your factors, or the interpretability of your factors, may help you decide whether it's, for example, 2 or 3. So I shouldn't be totally dismissive and say it has nothing to do with that, but that's like at the interpretability stage. If you're taking a data-based approach, it has nothing to do with it. Yeah.
So there are underlying linear combinations underlying each eigenvalue, right? So
There are underlying linear combinations?
for each eigenvalue.
Yes.
And so for each pair of the data set eigenvalue and by chance eigenvalue, the underlying linear combination may not be the same.
Correct. The weird thing is it's hard to think about the linear combination for the parallel analysis because there are actually 500 of them. And so what does that even mean? The average one, maybe? So I think the answer to your question is yes, but it's a weird thing to think about because one is from your one data set and the other one is from 500 looks at your data set.
So they are just ordered by how large is it, and then we compare each.
Yes, correct. Other questions? Okay. So now if you actually want to run the factor analysis, you would go to configure analysis, and now you would select a number of factors. Let's do 2. Now, here I actually wish it aligned better with SPSS because I don't have... Of course you can run a PCA, but we already know from PCA that it's going to be more noisy. And we already have a noisy data set because of the small sample. So I actually would be hesitant to run principal components analysis, but I wish they had principal excess factoring. Maybe they do, but it has a different name or something. So if I had to choose anything, I'd say unweighted least squares in this instance, but you might choose something different. Maximum likelihood, I like maximum likelihood, so maybe that. Maximum likelihood, though, assumes normal data, and unweighted least squares does not. And so I would probably be more comfortable not assuming that.
There's also this principal component analysis. Very confusing.
Yes.
So
Well, it's confusing if you try to make a distinction.
Yeah.
I don't. So it makes perfect sense.
And you won't ask us to make a distinction based on.
No. I mean, it's a distinction without a difference. I mean, it's not helpful.
is it maximum likelihood assumes?
Normality. Oh, I didn't point it out before, but notice you have a lot of options for rotation. We didn't actually run it before. I'd probably run it with Promax because that's the one that I'm most familiar with. But I mean, there are, what, 20 of them in here? I can't tell you about all of them. So I'm going to go with one that I know, which is Promax. But you may very well, in your experiences, have come across one that you prefer, assuming you have a good reason for it. Go for it. Yeah.
It doesn't have to be perfect one now, it's just acceptable.
Yeah. The more normal it is, the better the answer is going to be. Wait. Yeah. Yes. So I'm ready to run this now. Anybody? Should we save factor scores? Why not? So now I'm going to compute again. So the top portions should be essentially exactly the same. It's possible that the parallel analysis is slightly different because it's a randomization process. So it's possible to get a different answer, although you want to do it enough, and 500 seems like enough to me, that your answer is stable. So I would be surprised if we got anything different. And in fact, we don't. And now we get into some familiar kinds of output. So we get the unrotated loadings with the communality. So those are the rotated ones, or sorry, unrotated ones. Here are the rotated ones. And it has built in where if it's got less than 0.3, it's just not going to show them to you, and that's to help you see the simple structure. So the only one that looks a little funky, according to what we might expect, is it looks like factor 1, National Symphony, String Quartet, Wagner Opera, Piano, Soccer Game, and Ballet. And notice it's not the soccer game that cross loads. It just loads on number 1.
You're very European refined.
Yeah, I mean, it does seem like, okay, maybe soccer's a little bit of a different sport. It's more artistic. And then we've got a nice second factor here. National Hockey League game, baseball, football, championship boxing, and then we've got a not piano. And the Kentucky Derby. It's funny, I would have expected the Kentucky Derby, if anything, to maybe cross a little bit.
When we did this last class, didn't we change all the missing to 5, not to 99? Because they were missing because. So that might be what.
And that's a crappy method.
Yeah, we just made up.
No, it was 5 because if we didn't change it, it didn't go to another value. Like if
It
they wanted to
started
leave it
at
as
5.
5, yeah.
So, yeah. I don't remember using those sliders before in Qualtrics, and so I was like, oh, sliders, that'll be fun. Apparently, you need to be a little bit hesitant about using them.
Tim?
Yes?
So this goes back to my question. So that negative loading for piano on factor 2, hypothetically, let's say it didn't have that primary loading at 0.7, and it just had the negative 0.3.
Mm-hmm.
When you were coming up with factor scores for individuals, would that subtract that loading negative? If I had
Yes.
you would remove from that person's aggregated factor score.
Yeah, I mean, if you, it's like a beta, so it's like that one would be negative, so it would be subtracting it away. Yeah. And that, trying to think if there's anything. It even gives us a residuals matrix here. That's kind of nice. It shows us that there's a little bit of skewness here. it gives us even more information that you can drill down into for the missing data, which is, I mean, you're getting a lot of information here. And I don't necessarily think all of it is important. But if you do want to investigate it, you can. Unlike a lot of standalone programs where they're quite limited, this one is giving you a lot. In fact, it's giving you a lot more than SPSS. Or at least, maybe there's more, for those of you that like to paste, maybe there's some magic command that SPSS does. I know that you can do a parallel analysis in SPSS, but I downloaded like the syntax for it, but you got to tinker with it a lot, and I found it hard. So there you go. Yes.
Could you determine if there's a higher order factor based on the factor correlation matrix?
Ah, good question. Where is that in here? Here it is. So this is saying that those two factors correlate at 0.167, which is pretty consistent with what we found last time too. Which would suggest that there's not a whole lot going on at a higher order. I mean, that's a pretty low correlation. But if you had a higher correlation, 0.4, 0.5, 0.6, 7, yeah, absolutely. The higher the correlation, the more likely there is something else out there that could capture both factors. Okay. There's one other thing I wanted to show you, but are there any questions on this? Okay. Here's the other thing that I wanted to show you, and it's really just pointing something out. It's in configure analysis, and it's this polychoric tetrachoric correlation option. And I'm not going to go through a whole demo for it, but I can tell you that is how I actually came across this software. Well, I needed to do a factor analysis, but my data were ordinal, and I knew they were ordinal. And a polychoric correlation is the kind of correlation that you run if you have data that are ordinal. And so, again, I was up against a wall there with SPSS, and so I was looking for something that could be done with it. And a polychoric correlation matrix, again, is for ordinal data. It's an appropriate way to handle ordinal data. A tetrachoric, which you see in parentheses there, that's if you have variables that are dichotomous. It's a special case. And so some of us, I know, are interested sometimes in having factors based on items that are 0, 1. And so finding a software program that can handle that was challenging, and yet this can do it seemingly easily. And so it can handle dichotomous, ordinal, or continuous data, and it's got this built-in parallel analysis. These are other methods. To be honest, I don't know anything about them. Parallel analysis is what I've heard the most about, and it's what I'm most comfortable with. It makes sense to me. So I like parallel analysis. So it's got all of this stuff. So this sounds like a little bit of an advertisement. I suppose it is. But it's... So there's this constant tension between programs that can do everything, but they're a pain and don't necessarily get into every single statistic that you wish you had when you do this particular analysis, versus specialized programs that are very good at that one thing, and they give you everything that you would want, but only for that one thing. And so this is an instance where, to me, if you have anything special, like a parallel analysis, or like 0-1 items, or just ordinal items, I would totally shift in gears and use this. And I know that there are some people that just want to learn one program that can do everything, and that's fine. But I use a lot of different software programs. SPSS for all the basic stuff. And then I use HLM, and Amos, and M+, and Factor.
Would all the items have to be dichotomous if you're going to run a tetrachord?
I would need to explore that a little bit more. I think it could actually be okay with a mix, but it might be a limitation, honestly. And it might be the kind of thing where you would generate two different matrices, one for your continuous variables and one for your ordinal or dichotomous variables, and then you might take this part and then this part and make your matrix and then input it. Because you saw you don't have to input raw data, you can input a matrix, and then just tell it that you're giving it a matrix. I don't know. I would try it a couple different ways, and I'd look in the documentation more to see what it says about it. That is a challenge. It's like, well, if you have a bunch of items that are 0-1 and then some items that are, on a 1 to 10 scale, what do you do? I don't have a straight answer for you there. Yes.
When you save the factor scores,
Oh.
are they hard to interpret since they're going to be like somewhere random all by themselves?
Should be. Oh, wait, is it here? No,
Or is it
it's
just in
here.
there?
I think it's here. No, where did it save them? I have seen this before. Maybe it's at the bottom where it assigns each case. Yes, here.
Okay.
So you would have to take this and you could handle it. It's going to be a little bit of a pain, for sure. Other questions on factor analysis? If I assigned you homework where you had to use factor, how many of you would have a major problem with that?
Could you email us the output in case I have to be able to run?
Maybe that's what I'll do. I'll have part of it be where you do something in SPSS and part of it where you interpret some output from factor. That's a good compromise. Yeah, I could give you the output file. That's a good point. Even better. Thank you. Okay, any other questions? We're done here, folks. I'll see you next Tuesday.
Congratulations on getting a grant, Tim.
Thank you.